Hi everybody, it's Matt,
And Max.
and we're going to give you a tutorial on OpenRocket. Alright, number one is we need all of our units to be the same. So go to Preferences, go to Units, and make them look like this. Pause the video if you need to do that. And yeah, moving on. Max is controlling the computer, I'm just talking, so I'll just be narrating what he does. There are a couple main parts: nose cone, body tube, transition. These are your core rocket pieces. All the other pieces are built up upon them. So we're going to start with a nose cone because, we got to start at one part of the rocket. Let's start at the top.
Alright, so for the nose cone, you're going to get a bunch of options in every dialog box that pops up. There's going to be a bunch of tabs, a general tab for everything. Some will have a secondary tab like a shoulder or fin tabs tab. Generally an override tab, this is for if you know your mass already. An appearance tab for changing how it looks, and a comment tab for adding details. There will also be a bunch of different things you can change: material, component finish, any dimensions, and shape parameters. In this case, we'll be going with a 12-inch nose cone with a base diameter of 3 inches. Wall thicknesses for all components will be 0.05 inches, and the material for the nose cone will be fiberglass.
The nose cone having a 4:1 ratio is very common, as this one has.
Next thing we'll be adding is a body tube. It has a length of 8 inches in this case, outer diameter again of 3, a 0.05 thickness as with everything else. Most of our body tubes in the past have been made out of blue tube, and we will continue with that today.
You might notice that we're generally only using the general tab because that's the most important one.
Going back, there's actually something we forgot on the nose cone, and that is the shoulder tab that was discussed before. This is essentially just a component that sticks into the body tube preceding it, which will allow it to interface better. So with a wall thickness of 0.05, we will go for a 2.9 inch diameter and a length of 3. Here you can see the nose cone shoulder. It's a good rule of thumb for all interfacing internal components like this to have at least one body diameter in length sliding into the preceding component.
It's basically a built-in coupler, and if you don't know what a coupler is, they're just the parts that connect the tubes. They're smaller than the actual tubes.
Exactly. Moving down from this, we have the transition piece. We don't always use these, but we'll just demonstrate one here.
They change diameter.
Yep. The length here will just be left the same. The fore diameter is automatically calculated for you, and the aft diameter we will remove off of automatic and change to the 2.26, which is roughly 54 millimeters. Wall thickness again will be 0.05. We'll be going with fiberglass for this. And again, there's a shoulder tab for this section. The transition has two shoulders, a fore shoulder and an aft shoulder. The fore shoulder is in front, the aft is in back. We will have another 2.9 and 3 inch shoulder in front, and because the aft is smaller diameter, we will have a 2.16 and 2.26 shoulder in the back. Again, thicknesses are important as they
Exist.
are small weights here and there that are easily forgotten about. Continuing downward, we have another body tube. This body tube will be the parachute tube. It's good practice to name your components just so they're easier for other people to see what they are.
Which means we should probably go back and name our first body tube.
Exactly. Again, this will be blue tube. In this case, we'll have 10-inch length, outer diameter already calculated for us, and a 0.05 thickness. So this tube we made before, we will rename the parachute tube, the payload tube, sorry.
We generally put payloads under the nose cone,
Yes.
as we're doing here.
So the progression so far is nose cone, payload tube, transition, parachute tube, and lastly we will have the booster tube. Booster tube is the tube that houses the motor.
It's the one at the bottom.
Again, this will be blue tube, very common building material for us in the past. In this case, it will be 15 inches long, and again, keep your thicknesses up to date. Now we'll move on to internal components, so basically the components that are not the three that we've showed so far. Firstly, we'll be adding a payload to the payload tube.
Makes sense.
Payloads and electronics are generally added as mass components. So you're going to click on the tube you want to add them in, and then add the mass component. They will all show up as subcomponents in the left-hand side.
We can treat them as this because they don't really do anything structurally. The rocket just thinks it's another weight.
We will call this unspecified component the payload, and we will label it as such. This will be a 5-pound payload for the purposes of this example. And we can make it arbitrarily long, which essentially moves the center of mass of our rocket. We can also move it around relative to the payload tube by changing this value at the bottom. For this purpose, it will be 6 inches by 2.5 inches, and will be 1 inch off the top.
Generally makes sense to keep it somewhere around the center because that's just how the payload generally is, somewhere around the center of the tube.
Moving down, the next thing we need is bulkheads for separation. We'll have a bulkhead at the top and bottom of the parachute tube. The easiest way to do this is to have one located at the bottom of this transition. So by clicking on the transition and adding a bulkhead, it will automatically be added to the bottom.
It's perfectly placed.
It will have a thickness of 1/8 of an inch or 0.125, and we generally in the past have made them out of plywood.
And if it isn't automatically in the bottom, go to the Position Relative to tab and click Bottom.
Similarly, to put one at the bottom of the parachute tube, we'll add one to the parachute tube like so.
Hey, it's at the bottom again. Yay!
Again, we'll be making this out of
Paper.
plywood, and we'll have a thickness of 1/8 of an inch. One thing to note is that the nose cone and transition are nicely interfaced with their pseudo couplers or shoulders, which are built in, but these two tubes have no interfacing right now. The best way to interface in this instance is to add a coupler. So adding a coupler to the bottom of the parachute tube is essentially clicking on it, adding a coupler. We'll be making it out of blue tube, the same material that we use for structural.
Surprise.
It automatically calculates the outer diameter as being whatever fits inside.
Smaller.
And we can add our universal wall thickness. And in this instance, because we want the rule of thumb length of 2.26 inches on each side, which is the diameter, we will need a 4.52 inch coupler.
It's like twice as long.
To center this around the points between the parachute tube and motor tube, we will offset this by 2.26 inches. Essentially, this just means that we have an equal amount on each side.
That's half of the length. Quick maths.
Adding parachutes is very easy, and again, it essentially treats them as just mass components. I don't exactly know why they're separated. I guess just if you don't have a parachute, you won't have a recovery system, and OpenRocket won't simulate a recovery. But adding a parachute is as easy as clicking on it, inputting the masses that recovery gives us, and basically just filling the packed volume that you have. In this case, we'll go for 8 inches by 2 inches, and have it be 1.5 inch offset.
You might notice that to add things in OpenRocket to the rocket, you click the button that is their title, and that is the majority of the work.
Yeah, it's a very simple program, especially once you know what you're doing. You can build a rocket quite quickly. Last thing we'll be adding to this rocket to make it fairly universally functional is a shock cord, which just simply attaches the parachute to the rest of the rocket. In this case,
via the bulkhead,
it will be just a 1/2 inch off. You can really make the volume whatever you want. It's up to recovery to determine these sizes. The last thing you should notice, now that we have a general rocket that is nicely filled, is that our stability is completely garbage. Stability is essentially the measure of the distance between the center of gravity and center of pressure, and you can see the center of pressure is nowhere on screen, so our rocket would just tumble indefinitely, be a hazard to everyone, so we need to add fins to balance this. Adding fins is... you need to add fins to balance this. Adding fins is as easy as everything else. Click on the parent component.
Press the fin button.
And there you go, you have a trapezoidal fin set.
We like trapezoidal fins.
They're easy to manufacture, easy to order, and they just work well for us. Generally, we've used fiberglass fins in the past. You can change the cross section, just a nice rounded one, better for airflow. This is roughly the thickness we've used. You can change it based on your design specifications. We're using 3 fins for this design, and there are a myriad of other options. Root cord, tip cord, height, sweep length, angle, and again, the position. We also have another thing called fillets, a fin tabs tab, and again the other tabs. Fin tabs are essentially parts of the fin that go into the rocket, which are not aerodynamic, but serve as mass components. And fillets are essentially structural components that sit on the outside of your rocket. They're a radiused feature that interface the fin with the rocket nicely.
It's like gluing. So
for this rocket, a good root cord length would again be the diameter. If you haven't noticed, a lot of rules of thumb are just make it a diameter. So we'll go with 2.26 in this case, a tip cord of 1.26. To keep things simple, a sweep length, which is the distance between the top of the root cord and the top of the tip cord of 1 inch, which will give us a nice square in the back, and a height of 1.2 inches. And as you can see, this gives us a nice reasonable stability of 1.35 with our center of pressure located behind our center.
Max, are there some ratios that govern fins?
Another general rule of thumb for fins is that the tip cord is less than your root cord. This is obvious because you want the stable part to be connected. Generally, the tip cord is about 1/2 to 2/3 of your root cord. So just keep that in mind. Okay, now we have a fairly stable, flyable rocket that is easily and quickly designed in OpenRocket. Thanks for watching.
Yeet!